Hello everyone. In this video we will continue to discuss topic 7.2 nuclear reactions, and in particular the general shape of the curve of the average binding energy per nucleon versus nucleon number, otherwise known as the binding energy curve. So, in the last video, we introduced this chart and we talked about sort of its main features, which you do need to be able to sketch, and we talked about its importance, right? It gives us the fundamental fact straight away that there are two ways of conducting nuclear reactions that will give you energy, or that will release energy from the form of nuclear binding energy to the form of kinetic energy, and those are nuclear fusion and fission. But I have contended at the beginning of this session and a couple times since that this chart is actually upside down, that fundamentally one of the weirdest things about binding energy and the most confusing things is that binding energy is defined in a way where higher binding energy means that more energy has been released. So in many ways, a better version of this chart, if we could go back and sort of make another version of this chart more famous than this one, would look like this. This is a chart that gets sort of energy right. So if you remember, early in the unit, we talked about atomic energy levels, and those were all negative, right? They start at 0, and then you have negative energies as you go down, and so when you drop to a lower energy level, you can release a photon or release energy. That's fundamentally how this works. When you undergo either nuclear fission or nuclear fusion, you're moving, right, to this area on the binding energy curve. And when you do so, you release energy, okay? So the classic curve has this inverted. You want to think about this as sort of the most stable nuclides. Those are the ones where you would release the least amount of energy undergoing a nuclear reaction. And so ultimately, you would normally think about that as at the bottom of a hill or a potential valley, to use the more technical term. This is sort of the stable state, and anything up here is less stable, or over here, okay? One question that sometimes comes up is sort of, if this is true, if this is the actual binding energy curve, how come there's any hydrogen or helium at all? That is, why is it that those elements aren't down here immediately? And sort of the chemical analogy of this is the idea of activation energy. And the fundamental idea is that in order to undergo these nuclear reactions, you actually need to get those nuclei close enough for the strong force to sort of take over. So even though there's a lot of energy to be gained, you actually need very, very, very high temperatures and pressures for the nuclei to be close enough to undergo these reactions in the first place. That's why they only happen in very controlled artificial situations or in natural situations like at the core of stars. That is, the repulsion between the protons in the different nuclei is big enough that you sort of need to overcome it and get it close enough for the strong force to take over. It's kind of like sitting sort of in a small valley at the top of an enormous mountain. You still need to sort of climb that hill to get out to go down the mountain. That is a pretty good analogy for this situation. And it also sort of illustrates why this curve is better drawn like this, even though the classic one, the one you want to be able to sketch, looks like this. One more version of this, one more way of saying this or seeing this is that when you go from a lower binding energy per nucleon to a higher binding energy per nucleon, it feels like you would have had to have added energy, right? Because of the way that these phrases are given, right? You would think lower binding energy per nucleon plus energy equals higher binding energy per nucleon. But that's actually not the case, and that reflects the fact that this idea of binding energy is sort of defined backwards. When you go from a lower binding energy per nucleon, something down here, to a higher binding energy per nucleon, you release energy. That's that sort of conceptually challenging inversion is related to this idea that the binding energy per nucleon should probably be drawn and represented negative in this sort of way.